Welcome everyone to this installment of the ICTS Virtual String Seminar Series. Today we are very delighted to have Edward Witten with us, and he's going to talk to us about deformations of JT gravity and random matrices. Over to you, Edward.
Thank you, Siddharth. And thanks for the invitation to give this lecture. And it's really nice that this technology makes it possible to give lectures even at a time when we can't travel. So as you can see, my title is Deformations of JT Gravity and Random Matrices. So the lecture is based on this paper that I wrote recently. And there's also a paper by Maxfield and Turiaci who did a similar calculation and also related it to three-dimensional gravity. And at the end of my talk, I'll briefly explain what Maxfield and Turiaci did. So as many of you already know, JT gravity is a simple model of two-dimensional gravity that contains the metric tensor and also a scalar field, often called the dilaton. And the bulk action is what I've written. What makes it so simple is that the action is linear in phi. So the classical equation for phi, which you impose if you do a path integral over phi first, is an equation for the metric tensor only, which leads to the model being solvable. So now what I've written is actually the version of JT gravity appropriate for ADS2. In other words, the cosmological constant is negative because of the +2 in the action. A -2 would have landed us into Sitter space. Because we're in ADS2, you might expect a bulk dual that would be an ordinary quantum mechanical system. In 2 dimensions, the boundary is one-dimensional, and a one-dimensional space-time is the space-time of an ordinary quantum system, rather than a quantum field theory. However, Saad, Shenker, and Stanford showed that JT gravity is not dual to a particular quantum system, but to a random ensemble of quantum systems. So the first part of my talk will be simply a review of this analysis by Saad, Shenker, and Stanford. Then I'll get to the sort of main part. We'll consider deformations of JT gravity in which we add an additional term to the action, and we'll show that the deformed model is dual to a deformed random matrix theory with a different density of eigenvalues. Then in the last part of the talk, I'll say a little bit about what Maxfield and Turiaci did on the relation to 3D gravity. So a quantum mechanical system can be described by giving just a Hamiltonian H, which is a Hermitian matrix. In the type of random matrix ensemble that's relevant for JT gravity, you consider all possible n by n Hermitian matrices H with a probability distribution that's the exponential of -n times the trace of some function of H. That's an unnormalized probability distribution. You normalize by dividing by the partition function. Such a model has a limit in which n becomes fixed, n becomes large with f fixed. That was essentially shown something like 47 years ago by 't Hooft by analyzing Feynman diagrams. Now, if I let the lambdas be the eigenvalues of H, then the density of eigenvalues is defined as a sum of delta functions supported at the eigenvalues. So for a particular H, there's a particular rho 0, which is a sum of delta functions. However, here we have a random H, and if you average rho 0 of lambda over H, you get what I'll call rho of lambda. And usually, well, for now, we want to consider rho of lambda in the large n limit. What do we want rho of lambda to be if we're going to get JT gravity? Well, if we know rho of lambda, we'd say that the large n limit of the partition function, see, the partition function trace e to the minus beta h, can be computed as a sum over energy levels, except that after averaging, there's a continuous distribution of energy levels rather than a discrete sum. So if we know rho of lambda, we'd say that the large n limit is this integral of e to the minus beta times the energy times the density of energy levels. So if we want to know what rho of lambda would have to be to agree with JT gravity, we should compute the large n limit of the partition function of JT gravity, and that will tell us what rho of e should be. Now, in the bulk description, so the worldsheet, sorry, the space-time of the boundary theory is a circle if we want to calculate the partition function of the quantum system. And then in the bulk description, we fill in the circle by all possible 2 manifolds. But in the large n limit, the dominant 2 manifold is just ADS2 itself, or topologically a disk. Or to be more precise, we're supposed to use large region U in ADS2. That's because it's been discovered that in 2-dimensional holographic duality, it's important to consider a slightly cut-off version of anti-de Sitter space. But anyway, to get the partition function, we do a path integral on a 2-manifold whose boundary is a circle where the quantum system lives. And for large n, that 2-manifold will be a disk. It's a disk with a wiggly boundary, and gravity comes in only in those wiggles. So what has been drawn is this disk in gray, this disk with wiggly boundary. And that path integral on the disk can be computed by a version of localization and gives this function I've written here at the bottom. So that's the partition function as a function of the inverse temperature. By an inverse Laplace transform, you can put it in the form of an integral over the density of states. And when you do that, you learn what should be the density of states if you're going to reproduce JT gravity. It should be this nice function, which is the exponential of a constant that comes from it's the ground state entropy. It comes from the Einstein-Hilbert part of the action, times this nice cinch function. So to get JT gravity, we take n to infinity, adjusting the measure so that rho of v converges to this function. And if we do that, by definition, we get a random matrix model that agrees with JT gravity, at least in the large n limit. So the process of taking n to infinity while adjusting f so that rho converges is called double scaling. The hypothesis then is that a double scaled matrix model with this rho of v is equivalent to JT gravity. Well, the way we test if this is right is by calculating in higher orders. To make it work at the lowest order, we simply pick the unique function rho of v that would make it work. But now we have a prediction for higher orders. After double scaling, the 1 over n expansion is replaced by a 1 over e to the s0 expansion. And the expansion comes from a sum over spacetimes of different topologies. So the average of the trace of e to the minus beta h on a boundary circle, a circle in the dual quantum mechanical system, is a sum over genus of contributions of spacetimes of genus G. So the disk was genus 0, and now we're going to add the higher topologies. And by counting powers of 1 over n, which becomes e to the minus s0, in Feynman diagrams, you learn that in genus G, the contribution will be of the order I've indicated here. So on the matrix model side, everything is completely determined once the large n density rho of e is given. That determines the measure of the matrix model, and then you can just calculate the matrix model integral however you wish. So we have to compare the 1 over e to the s0 expansion of the matrix model to the topological expansion on the gravity side. What makes the gravity part of the calculation possible, in part, is something I mentioned before. The action of JT gravity is linear in phi, so a path integral over phi is going to be elementary. So here I've written the path integral, well, I just wrote the integral over phi. Well, you integrate over phi after rotating the contour to imaginary values, and then the phi integral is a delta function that sets r plus 2 equals 0. So if we were on a compact Riemann surface sigma without boundary, integration over phi would reduce us to metrics with r equals minus 2. But every complex Riemann surface has a unique Weil factor that makes r equals minus 2. So the space of such metrics up to diffeomorphism is just M sub G, the moduli space of Riemann surfaces of genus G. Now, when you do this integral over phi, you get a delta function. When you evaluate the delta function as a function of the metric, you'll get a determinant. But you can show that on an orientable spacetime, the determinants cancel. And so in the end, the path integral just computes the Weil-Petersen volume of m sub g times this factor that comes from the Einstein-Hilbert action. I'll call the volume V sub g. Now, we're not in exactly that situation when we're trying to compute trace e to the minus beta h in the dual quantum mechanics, because now there is a boundary, and the boundary is in an asymptotically ADS2 region. So the space-time looks more like this. There's a genus G surface, where in this picture, G is 2, but there's also a boundary. And metrically, since the boundary is asymptotically ADS2, the metric blows up near the boundary, so that's kind of been sketched here. But you can build this space-time by cutting on the smallest possible geodesic that separates the boundary from all the topology. So if sigma is a genus 1, well, I wrote here genus 1, but the picture is genus 2. If sigma is a surface with a single ADS2 boundary, it can be built by gluing what's been called a trumpet U prime to a genus G surface sigma prime with geodesic boundary along their common boundary, which is the geodesic of length B. And the path integral can actually be split into two parts: a path integral on the left, a path integral on the right, and an integral over B. So the relation among path integrals that goes with the picture, and this is one of the key steps of Saad, Shenker, and Stanford. The full path integral, you have to integrate over all possible choices of B. And the measure is B dB, where the extra factor of B comes because there's a relative twist angle between the two sides, which gives a factor of B. And then what you have to integrate over B is the product of the path integral on the left and the path integral on the right. And so the way you deduce this simple formula is by first integrating over phi, which reduces to simple statements about gravity. And then the gravity discussion takes this form. So of these two factors, so one is the path integral on the trumpet. The other is the path integral on a Riemann surface with one boundary, about which we otherwise know nothing. The path integral on the trumpet is another path integral that can be computed by localization. So there's an explicit formula for it. And as for the rest of the surface, it's complicated, but the same argument as before, after we integrate over phi to get a delta function, shows that it's again a Weil-Petersen volume. Okay, I wish I'd written V G comma B. So it's the volume of the moduli space of genus G Riemann surfaces with one boundary of length B, except I wrote 1 for the genus. So what? It's the volume of mg sub B, the moduli space of hyperbolic Riemann surfaces. A hyperbolic Riemann surface is a Riemann surface with the metric of r equals -2, which we get from the delta function, of genus 1 with a boundary of length B. So more generally, JT gravity on a surface sigma prime with any number of geodesic boundaries of given lengths. The path integral is what I'll call V sub GB, the volume of the corresponding moduli space of genus G surfaces with the B boundaries of given lengths. So luckily, the volumes can be computed by a recursion relation that was discovered by Maryam Mirzakhani, the Iranian woman who was the first female Fields medalist. And moreover, this recursion relation is equivalent to a particular method of calculating matrix integrals that was developed by Eynard and Orrington and called topological recursion. It's a sophisticated modern version of the loop equations that are familiar to veterans of the matrix models from 30 or more years ago. And Einard Norrington showed that Mirzakhani's recursion relation is the recursion relation of a certain matrix model. And the key technical observation of Saad, Shenker, and Stanford was that the two matrix models coincide. The matrix model that computes volumes, according to Mirzakhani and Einard Norrington, coincides with the one that's associated to the density of states rho of V that comes from the JT path integral on the disk. Maybe I'll stop here for, that completes the first part of the talk, what I'll say about the work of Saad et al. So perhaps it's a good moment to stop for questions, if there are any. Not hearing any takers, I guess I'll go on to part 2 of the talk. And
sorry, Edward, can I just ask one small question to you, which is tangential? Hello?
Yes?
We rotated the contour of the dilaton for this whole calculus. Insofar as you might try to get JT gravity from a dimensional reduction where the dilaton is, say, the radius of a two-sphere or an internal volume, you might want to do the integral in a different way by keeping it real but cutting it off, say, at 0 value.
Yes.
And would this change some of the story in an interesting way? As I said, it's tangential, but I just thought I'd ask.
Good question, which I don't think has been properly studied. Hopefully it doesn't change it very much. Because what you're saying is more physical. So what I described which, gives efficient answers. And hopefully it approximately agrees with the more physical procedure that you'd follow in a more physical model. I can't make any guarantees.
Okay, thank you.
Any other questions? Okay, in that case, we'll go on and try to generalize the JT gravity matrix model correspondence to a larger class of models. So we'll consider deforming the action of JT gravity by adding additional terms. Now, I'm going to assume we want an action that we don't add additional fields, so we'll only have a metric tensor G and a scalar field phi. And I also will assume that we don't want more than 2 derivatives in the action. So under those assumptions, the most general possible action is what I've written. There are 3 functions: a function multiplying the scalar curvature, a function multiplying the kinetic energy, and we could replace the 2 phi that we had in JT gravity by any function of phi. However, 2 of the 3 functions can be eliminated by a Weyl transformation of the metric and a reparameterization of the scalar field phi. So you can actually reduce to a single function and just consider this model. And that's suggestive because a matrix model would have also involved a single function of a real variable, the density of states. So maybe the 2 families of models will match. So here's a question: which of these more general models are matrix models? Well, a reasonable guess is that they all are. We have a family of models depending on a single real valued function W of phi, and matrix models are likewise defined by a single function rho of V. So a reasonable guess is that there's a mapping of some kind from one function to the other. Now, we need to accompany this guess with a warning. If there is such a mapping, its detailed form depends on a procedure for how you're going to regularize and renormalize the theory. In other words, it's not meaningful to say how rho of V is supposed to be related to W of phi without first saying exactly what procedure is going to be used to define the quantum theory. Part of the complication of quantum field theory is that a classical Lagrangian doesn't really define the theory. Well, this is true even in quantum mechanics because of all kinds of operator ordering problems. You'd say in quantum mechanics, there isn't a one-to-one mapping from classical problems to quantum problems. You have to explain how you're ordering the factors. In quantum mechanics, in quantum field theory, you additionally have to explain your procedure for regularization and renormalization. So I'm going to explain a particular procedure to define the theory, which from some points of view, isn't that natural. For example, it doesn't make manifest the classical limit. But from other points of view, it's useful because it leads to efficient calculations. And with that particular approach to defining the theory, I'll explain that, roughly speaking, every W phi corresponds to a matrix model. There's some fine print in the statement about every one. So I'll usually write that W is 2 phi plus some function U of phi, where we would have 2 phi in JT gravity. So U of phi is the correction to JT gravity. It turns out that for a specific method to define the theory, you can get a rather general answer for rho of V. For example, if I impose one condition U of 0 equals 0, which is just one condition on the function U, then you can get an explicit answer, which I've written, or an explicit and simple answer. So with the procedure I'll explain, as long as U of 0 is 0, this is the exact answer. If you want to know what 0 really means, 0 is the dilettante value for an extremal black hole in JT gravity. So the hypothesis that U of 0 equals 0 really means that you're trying to avoid modifying the extremal black hole, or at least you're not modifying the threshold value of phi in an extremal black, the horizon value of phi in an extremal black hole. Anyway, under this condition, there's a simple answer for rho of V. If U of 0 isn't 0, you can still write an explicit formula, but it's much more complicated. And so I won't actually write it down in the talk. You can look it up in the papers. Now, there's some fine print. This formula is valid, well, technically for a large class of U's. I don't literally prove it for every U, but morally it's true for all U's, to all orders in perturbation theory in U. But it can't be an exact formula because positivity of rho of E can be lost if U is sufficiently large and non-positive. You'll see that if U is everywhere positive except at 0 at phi equals 0, so that the formula is valid, then rho is everywhere positive as well. But if you take a U that isn't everywhere positive for real phi, and moreover, if U is sufficiently large, then positivity of rho is lost. And so the formula must eventually break down. My guess, but only really a guess, is that the formula is valid for a non-zero range of U, but breaks down at a first order phase transition before positivity would be lost. On the other side of the phase transition, I would guess there would be what in the old days was called a two-cut matrix model. That's a matrix model. I didn't emphasize this, but in JT gravity, the rho of E is non-zero on a whole half line. That's called a single cut. You could instead have a model where on the real axis, there's a semi-infinite interval with eigenvalues and also an isolated cut with some eigenvalues. That would be called a two-cut matrix model. So my guess is that when U of E becomes bad and this formula breaks down, you'll have a first order phase transition to a multi-cut matrix model, but don't have a good method to show that at the moment. Now, it turns out that it's convenient to first consider the special case where U is a simple exponential function of phi with a coupling constant that I'll call epsilon and an exponent alpha, with some suitable restrictions on alpha. Now, classically, the obvious condition is that alpha should be positive, because usually in deforming JT gravity, we wouldn't want to change what's happening at infinity. But near the boundary of the asymptotically ADS2 space, which is what I mean by AADS2, near the asymptotically ADS boundary, phi goes to plus infinity. So I don't want a perturbation, classically I'd say I don't want a perturbation that overwhelms what is already there near the boundary. So positive alpha is fine because this vanishes exponentially near the boundary. Negative alpha would be a perturbation that dominates near the boundary. And then that would mean that the ultraviolet behavior is completely different from JT gravity. So if we want a model that looks like JT gravity at high energies, we'd say alpha should be positive. Now, for technical reasons, it's useful to put a stronger condition on alpha, but I'll postpone that for a moment. Let's look at the path integral with this perturbation. So I've written the path integral now over phi and g, and I divide by the volume. I've got the exponential of the action of JT gravity, but I've also added this additional term to the exponent. And now I want to do perturbation theory in epsilon. So to do perturbation theory in epsilon, I take the exponential of epsilon times this interaction, and I expand it in perturbation theory. The first term involves an integral of the perturbation over the space-time sigma. The second term is a double integral over 2 copies of sigma, and so on. Now, once we make this, okay, the reason for making the expansion is the following. Since the original action here is no longer linear in phi, we can't do the path integral over phi. But order by order in the expansion, we can do the path integral over phi again. Because, for example, let's look at the term linear in phi, which is just by given just the product of this function times the exponential of the JT action. So the linear term has an integral over the space-time integral d2x naught, and also a path integral. I've pulled the integral over the space-time out here, so I'll do that last. Then I have an integral over phi and g, and I have the exponential of the usual action, but there's another term which is minus alpha times phi of x0. That comes because it's sitting here, e to the minus alpha phi of x0. We have the product of 2 exponentials. One is the JT action, and the other comes from the perturbation. So putting them together, we have the exponential of the action minus alpha times phi of x0. So now we're back to having an exponent that's linear in phi, so we can do the integral over phi. And now we get a delta function, but it's supported not at r plus 2 equals 0, but at r plus 2 equals a delta function of x0. And this means that we get not a smooth Riemann surface with a metric of constant curvature of -2. We get a hyperbolic Riemann surface that has a conical singularity at x equals x0. And alpha determines what's called the deficit angle, the missing angle. So we have a conical singularity. I should have on the slides drawn a cone, but you can imagine a cone with a missing angle alpha. So I think I have pictures later of such things. So our Riemann surface is now not a smooth Riemann surface with r equals -2. It has instead this conical singularity at x equals x0. And that's a good description if alpha is less than 2 pi. If alpha is bigger than 2 pi, there's no real solution. And we need to find some slightly different method to evaluate the path integral. So we'll continue assuming alpha is less than 2 pi, but later it'll turn out that it's easier to calculate if alpha is bigger than pi. So our calculations are really valid in the range that pi is between alpha and 2 pi. Sorry, that alpha is between pi and 2 pi. But the answers we get are analytic in alpha, so presumably they're valid outside that range. In higher orders in epsilon, we'll have not a single conical singularity, but any number of such singularities. If there are k of them, they come with the factor epsilon to the k over k factorial. So that was, for k equals 2, that's present here. For k equals 2, we have a double integral over sigma, and there will be new terms in the exponent at x equals x1 and x equals x2. And so we'll get a Riemann surface with 2 conical singularities and a factor epsilon squared over 2. With k conical singularities, it would be epsilon to the k over k factorial, where the 1 over k factorial means that the conical singularities are indistinguishable, and each one comes with a factor of epsilon. Now, the path integral, for example, on a compact Riemann surface with no asymptotically ADS2 ends, still computes the Weil-Petersson volume of the moduli space, but now this is the moduli space of hyperbolic Riemann surfaces with conical singularities. So maybe I'll stop just a moment again for questions.
Hi, I have a question. Could you please go back to the previous slide? So I was wondering in the top line where you put the square root g on the outer integral, but
Yeah.
the inner path integral is integrated over all metrics. I was wondering, I mean, what, I mean, this is probably a very pedantic question. So what that implies as a path integral statement when the metric at x naught is pulled outside.
You're correct that this is, as written, isn't quite correct. The square root of g should have been written here, or else the dg could have been put over here on the left. The important thing is I want to do the integral over phi first.
Yeah.
Integral over phi gives us, localizes us on metrics of this kind. What do we have after that? After that, we're integrating over all metrics, but we're also integrating over the choice of a position on the Riemann surface. So after we've integrated over, we divide by diffeomorphisms. So we'll, after integrating over phi and dividing over diffeomorphisms, then we'll be integrating over all choices of Riemann surface together with a point x0. So that's the moduli space of Riemann surfaces with one puncture. Except these Riemann surfaces will have not just a complex structure as is usual in string theory. There will be a conformal choice of the metric, a Weil factor chosen that satisfies this. However, you're correct that the formula was written somewhat imprecisely.
Thank you very much.
I have a question, Edward.
Yes.
So instead of taking u to be an exponential minus alpha phi, suppose I take u to be phi square times e to the minus alpha phi. Then these calculations cannot be really done because of this phi square in front of e to the minus alpha phi.
That's true.
Is there, I mean, how do you get around it actually?
Well,
because
if
in the
I literally wanted to do that, I would do the integral with the e to the minus alpha phi as a function of alpha, and then differentiate the answer twice with respect to alpha. So that's how I would do that one.
Okay.
I actually have a question.
The other question I had is the following: that so you have a deformation of JT gravity by this function. Now we know that JT gravity without this deformation maps onto the SYK model actually, because by the usual approximately. Now, is there some deformation of the SYK model that will correspond to this U of phi, some operators which we can introduce in the SYK model which will correspond to?
Good question, I don't know. The SYK model, it's only the Schwarzian sector of the SYK model that matches to GT gravity. So
yes, yes, that's true.
Possible interpretation of your question is whether whether what I'm describing could be matched to deformed versions of the Schwarzian path integral where you add higher corrections.
Yes, that's the question.
That's a version of the question. I haven't thought about it. I can't give a useful answer, I'm afraid.
Oh, okay.
Any other questions?
Thank you.
Are these conical singularities allowed to coalesce, or they are not relevant even if they coalesce?
Well, an algebraic geometer would say by fiat that they can't coalesce.
I see. Exactly why is that so? Is it evident from the formulas?
Well, I'm going to give a different answer.
Okay.
See, in the path integral, we get the Weil-Petersen volume. And that's given by a measure. And the measure, okay, there's an actual measure which you want to integrate over moduli space. The integral converges.
Okay.
And the set where the two would coalesce is a set of measure 0. And since the integral converges, it doesn't matter whether you can include it or not.
Okay.
So if you work directly from the path integral, the answer is the second one I just gave you. That it doesn't matter because the path integral the measure you get converges.
Mm-hmm.
But although that's a correct answer, to directly calculate the integral that way can be hard. And sometimes you want to make contact with things that algebraic geometers know. And then it will be used. Algebraic geometers have very fancy methods to calculate. In that language, by fiat, they can't, the conical singularities don't meet. So,
okay, yeah, thank you.
There's a powerful method of calculation where they're not allowed. See, in algebraic geometry, you would not have a distinguished measure you want to integrate.
Yes.
You'd only
Yes.
have a homology class.
Yes.
And therefore, it's important to compactify.
Yes.
The compactification is achieved.
Okay, so the compactification will get rid of this.
Well, see, the answer to your question from the point of view of algebraic geometers is that the compactification is achieved without letting the points coincide.
Yes.
But that's not obvious to the naked eye. To the naked eye, it appears that you have two singularities that could be close.
Yes.
And if you don't coincide, it looks like you get a non-compact space.
Yes.
But Deline and Mumford showed that a better way to look at it is that when they are almost coinciding, the surface is splitting off a different component. So in that approach, you compactify with the points never coinciding. But what's closest to the physics here is just to measure where the integral converges. You don't have to ask the question. The question really comes in when you, if you want to borrow, the question only comes in if you use a method of calculation, you want to borrow results from algebraic geometers.
Nice. Yes.
Okay, maybe I should.
Thank you very much.
Sure, sure.
So can I ask one question related to maybe is it true that if the punctures coalesce, that's the same problem as having contact length?
Yes, roughly, morally at least. Yes, I said at the beginning that the mapping from classical actions to quantum theories isn't unique, but depends on a procedure. And I didn't want to go into a lot of detail, but the trickiest part of that, well, one part is that you'd have to renormalize the perturbation you're trying to add. But even after you do that, when you do perturbation theory and you have multiple insertions of perturbation, they could meet. And then you get potentially ambiguous contact terms. So the answer to the last question really involved explaining the recipe for answering all questions about contact terms. So I gave two versions of it. The more physical was that the measure converges.
Okay, thanks.
In this particular approach, there aren't any bothersome contact terms. And then there's the algebraic geometers version, where you legislate that contact terms aren't allowed. But anyway, now we've explained exactly what we mean by the theory associated with this exponential interaction. So that makes the rest of the discussion well defined. But it won't necessarily agree with another procedure by which you would have defined the same interaction. Yes, Vladimir?
This is Volodya Kazakov. Hi. I wanted to give some comment on this model. So as far as I understand, this is a model of two-dimensional manifolds which are flat except of a gas of conical singularities, yes?
Yes.
I wanted to say that once back in the 90s, we solved such a model even on the lattice using a specific matrix model, which we called the model of dually weighted graphs with Matthias Staudacher and Thomas Winter. We modeled singularities on the by simply lattice defects, and we solved exactly this model, found the algebraic curve. So maybe it's useful, and because
it looks like it might be. What values of the defect angles did you have, or was it arbitrary?
Yeah, actually, we had fixed values, say pi over. The rationals of pi, some rationals of pi. Like we have 3 triangles instead of 4, 3 squares instead of 4 at some vertex, etc. But in principle, it can be developed further, and you can model different kinds of defects.
That's interesting. As I'll describe at the end of my talk, Turiaci and Maxfield have specific angles, which probably are some of the ones that were simple in your construction.
Yeah, there are specific angles, but modifying this model, you can get a mixture of these angles, etc.
That's one way
the
to go.
advantage is that you solve it from the lattice precisely.
Okay, I'd like to learn more. Okay, maybe I should go on now, though.
Sure.
So Now we want to compute the effects of the perturbation on the density of eigenvalues. So for that, we have to do a path integral on a disk, but now with any number of conical singularities on the disk. So in the lowest non-trivial order, there's just one singularity. But, okay, here I finally draw on a conical singularity. Okay, that's a cartoon version of a hyperbolic disk with a conical singularity at the bottom. So the moduli space of a disk with a single conical singularity consists of only one point. So there's no moduli space to integrate over. And so the path integral really reduces to a Schwartzian path integral over small fluctuations of the boundary. And this is another path integral that can be done by localization with a result I've written. So we get a formula for the path integral on the disk, including the first non-trivial term in powers of epsilon. Now, suppose we had a more general function, not a simple exponential, but a sum of exponentials. Well, in first order, we just add the linear effects of all these perturbations. So to first order in the epsilons, the partition function would be what I've written here, the sum of what we had on the last slide over all values of I. And you can take an inverse Laplace transform to turn this into a density of energy levels, and you find that this is the density of energy levels to first order in U. I wrote as claimed earlier, but I didn't quite claim it earlier. What I said before, I said before that if U of 0 is 0, this is an exact formula with no order U squared. That's also true, but that's one true statement. That's a statement I made before. But another statement is that regardless of any condition on U, at least for any U of this kind, to order epsilon, or to linear order in U, the density of eigenvalues is what I've written. Now, this formula was derived for this class of functions, sums of exponentials, which isn't literally any function. But the answer can be written universally in terms of U, as I've done here. So I imagine it's valid more generally for probably for any U for which the question makes sense. But the derivation is only for the class of U's I've actually written at the top. Now suppose we want to go to higher orders in U. We'd like to imitate the factorization used by Saad, Shenker, and Stanford in going to higher orders in the topological expansion. Remember, the idea was that a hyperbolic Riemann surface with asymptotically ADS2 boundary can be obtained by gluing a trumpet onto a compact surface with geodesic boundary. The way you get this factorization, I just wrote down the picture before without explaining why it's true. You start with a closed loop that's homotopic to the boundary. Then you minimize its length. Among all loops homotopic to the boundary, there's a unique one of minimal length, and that's the desired geodesic. The minimum always exists and is unique. That's a property of negative curvature, and it's the geodesic along which you want to cut. Similarly, if we have a disk with asymptotically ADS2 boundary and n conical singularities, we want such a factorization. So here, not sure how well it's drawn. C is the asymptotically ADS2 boundary. Then we have some conical singularities. I've drawn a case with 5 conical singularities. And I want to start with a circle homotopic to the boundary, minimize its length to find a geodesic, which in this picture is called gamma. And if the minimum exists, then a disk sigma with asymptotically ADS2 boundary C can be built by gluing a trumpet sigma prime to another surface sigma double prime. That assumes that the minimum exists. Also, without gamma jumping over any of these, you want the minimum to exist while gamma stays to the left of all of the singularities, so that the trumpet here doesn't contain any of the conical singularities. So in this example, sigma double prime is a disk with 5 conical singularities and geodesic boundary gamma. If such a decomposition can be made, the path integral on sigma is the product of path integrals on sigma prime and sigma double prime, integrated over the length b of the geodesic with measure b dB. Sigma prime is a trumpet without conical singularity, so its path integral is known and was already used by Saad, Shenker, and Stanford for JT gravity. On the other hand, the path integral of sigma double prime is another volume. In this case, it's a volume of a moduli space of Riemann surfaces that have conical singularities, as well as a geodesic boundary. So if the decomposition exists, we can sort of give a general formula for the path integral on sigma. Well, in writing it, I'm going to use this class of u's here. So u is a sum of different exponentials with amplitudes epsilon I, and each exponential will produce a conical singularity alpha I. And we have to sum over which type of conical singularity is at each of the 5 points. So I sum over all choices of labeling of the marked points by value of alpha. I divide by k factorial because they're equivalent. I multiply by the exponential of S naught because we're on a disk. I integrate over B, and then I have the path integral of the trumpet, and I have the volume factor, which is the path integral on the rest of the Riemann surface. So this is the path integral on sigma, at least if the decomposition exists. That's actually a useful answer because there are effective methods to compute these volumes. But I won't really have time to explain that in general, but I'll just calculate for you in second order. So in second order in U, we have a disk with a geodesic boundary of length B and 2 conical singularities. The moduli space is a point. The volume is 1. So this factor goes away. And the contribution of the partition function can be evaluated explicitly. We have to do this little integral, and we sum over I1 and I2, and we get what I've written on the right-hand side. Now, I use the fact that for U of this kind, the sum of the epsilons is U of 0 over 2. Now, before saying more about this answer, I want to discuss one step in the derivation. So we needed to be able to decompose our Riemann surface in this way. And we find it by minimizing the length of a loop that's homotopic to the boundary. And hopefully, when we achieve, first of all, hopefully the minimum exists. And secondly, hopefully the minimum is such that there are no conical singularities in the left region. It's not hard to convince yourself that the minimizer exists if and in general only if the alpha I are large enough. So this picture is meant to convince you that condition on the alphas is needed. Here I've drawn a hyperbolic disk with 2 conical singularities. And you should imagine starting with a loop homotopic to the boundary and trying to minimize its length. Well, in the case I've actually drawn, it's not clear a minimizer exists because it looks like it'll be favored to move the loop all the way up to the singularities and then even jump them across and let it shrink to 0. So if the deficit angles are very small, the minimizer won't exist. The geometry of the disk is almost that of ADS2. In ADS2, there are no closed geodesics. And having, so in ADS2, if you start with the loop homotopic to the boundary and try to minimize its length, it'll just shrink to a point. And the same thing will happen in the presence of conical singularities that are too weak. The loop will just shrink, pull across the conical singularities and shrink to a point. However, if the conical singularities are strong enough, the geometry looks more like this, where the surface bends outward again, and the minimizer will exist. And it turns out that the dividing line is alpha equals pi. So if all the alphas are bigger than pi, the minimizer exists. and our method of calculating the path integral works. So the formula we get makes sense even if the method doesn't, and it might be valid in more generality. But the derivation requires that the alphas are equal to pi.
Edward?
Yeah.
Sorry.
No problem.
So it would seem like what should matter is the sum of all the deficit angles. But
that's actually not right, though. Suppose one of them is very mild, but the other is a strong. Or suppose we add to this picture one more conical singularity with a very small deficit angle. It could be anywhere, so it could be here. Can you see my cursor? It
yes.
could be here, but it also could be here. So
Okay.
if I add a very mild conical singularity that's over here, if I try to find the minimizer, gamma will have jumped across over the mild singularity, but it will be stuck before the strong ones.
I see.
So in general, a minimizer with all conical singularities to the right of the minimizer only exists if all the conical singularities are strong enough.
Thank you.
Sure. Any other questions?
Yeah, sorry, I see a raised hand. Can I ask Arpita to please unmute your mic and ask your question?
Sorry. There is something problem.
We can hear you now. So
Sorry, I don't have a question.
okay. I'll go on then if there aren't more questions.
Sure, please go on.
Now I want to discuss the physics a little bit of this formula. So we derived this formula for the second order correction, but then I went into this technical detail of when the derivation is valid. But now I want to instead discuss the physics of this formula. Let's go back to the answer in JT gravity. The threshold is at 0 energy, and near threshold, the density of states is proportional to e to the 1/2. That's not an accident. In Hermitian matrix models of the relevant type, the threshold behavior is always that rho of e is of order e minus e naught to the 1/2, where e naught is the threshold energy. Now, let's look at the order U correction. The order U correction has the desired threshold behavior if U of 0 is 0. Because, you see, well, first of all, we're at risk because we've got a 1 over root e. But if U of 0 is 0, then that'll cancel the singularity. And this order U correction will go as e to the plus 1/2. So if U of 0 is 0, the threshold behavior is unchanged, and it's conceivable for this to be an exact formula. And it is exact, although I didn't prove it, and I won't prove it in the lecture. What I did show you was that in order U squared, there is no further correction, provided U of 0 is 0. But in fact, all higher order corrections are proportional to U of 0 squared. And the formula is exact, at least all orders of perturbation theory, if U of 0 is 0. But if U of 0 is not 0, it's clear that there has to be a correction, because, you see, this order U term does not have the right threshold behavior. The order U term is proportional to e to the minus 1/2 instead of e to the plus 1/2 if U of 0 is non-zero. The only way to reconcile this with the expected threshold behavior of a matrix model is to interpret what we're seeing as the first two terms in an expansion. So suppose the threshold energy is not 0, but is some constant E0, then E minus E0 to the 1/2 would be E to the 1/2 minus E0 over 2 E to the 1/2 plus higher orders that are even more singular at e equals 0. So we can interpret this term here. If we hope that the model is a Hermitian matrix model, even when U of 0 is non-zero, we have to interpret this term as representing a shift in the threshold energy, so that the threshold energy is no longer 0, but it's minus U of 0 plus order U squared. But in this case, there have to be further corrections, because in order U, all we've seen is the first two terms in this expansion. And if E0 is non-zero, the expansion goes on forever, and we need to see the higher terms just to get the right threshold behavior. In fact, the order U squared term that we computed, which was this, When you convert it by inverse Laplace transform to a contribution to rho of E, precisely it represents the quadratic term in the expansion of E plus U to the 1/2 in powers of U. So the order U squared term is the minimal possible term that's consistent with expecting to get the threshold behavior of a random matrix theory. And you can show that all the higher order terms similarly are dictated by trying to get a random matrix theory. So the quadratic term was the minimal possibility given the hypothesis that the model is equivalent to a Hermitian matrix model. And as I said, something similar works to all orders in U. So I could have planned to, well, use the remaining time to explain that rather technical story, but instead I'm going to go in a rather different direction and make contact with the work of Maxfield and Turiaci. But before that, there's an aspect of JT gravity and its generalization with conical singularities that'll be important, so I want to point it out. So the work of Saad, Shenker, and Stanford did not consist of evaluating contributions to the path integral associated to classical solutions only. For example, the averaged partition function of the boundary quantum mechanics received contributions from bulk Riemann surfaces of arbitrary genus with one asymptotically ADS boundary. Even though if you try to solve the classical equations of motion and the boundary conditions for phi, you'd find that this is only possible for genus 0, disk. In the work of Saad et al., the first step was not to solve the equation of motion for phi, but to integrate phi out. And in general, they got contributions from integrating phi out, which can't be interpreted as contributions of classical solutions. There's something similar to the relation of gravity to include conical singularities. In linear order, we consider a disk with one conical singularity, and it's possible to solve the classical equations for phi together with the boundary condition. In quadratic and higher orders, there's a disk with two or more conical singularities, and it's no longer possible to solve the classical equation and satisfy the boundary condition. The classical equation says that phi is what's called the moment map for a killing vector field that, given the boundary condition, has to generate a rotation of the disk. But a disk with two or more punctures has no rotational symmetry, so we can't solve the classical equation. Now remember, we learned that when U of 0 is non-zero, terms quadratic and lower order in U are important for getting a sensible threshold behavior in the dual matrix model. So we learned that to get physically sensible answers, you have to consider contributions to the path integral from sectors of field space in which it's not possible to solve the classical equations of motion. So that's simply a fact about the calculation I've already explained. But the reason I've dwelled on this fact is that it's going to be important background for what I will say about the work of Maxfield and Turiaci. So I'll use the remaining time to explain a little bit about what was done by Maxfield and Turiaci. They did an analysis of JT gravity somewhat similar to what I've said so far, but importantly, they related it to a question in 3D Einstein gravity. Let's first discuss 3D Einstein gravity. The ADS-CFT correspondence suggests that Einstein gravity in 3 dimensions is dual to some 2D CFT. Trying to gain information about the CFT, Maloney and I, more than a decade ago, tried to compute the partition function of this CFT on a Riemann surface of genus 1. To do this, you're supposed to sum over contributions from all 3 manifolds X of boundary sigma. Now, the meaning of the Euclidean path integral of gravity isn't terribly clear because it's, for example, it's not convergent because of the conformal factor, which has an action of the wrong sign. Gibbons and Hawking had suggested that it should be interpreted as the sum of saddle point contributions. So partly motivated by this, but also partly motivated by the fact that it was all we could do, we assumed we should only consider those x's with boundary sigma, such that there exists on X a complete solution of Einstein's equations with sigma as conformal boundary. It turns out you can find all the x's in question. They're solid tori. So for any choice of decomposition, so remember sigma is a 2 torus, genus 1. So sigma is a product of 2 circles, and then X can be the product of a disk times a circle, otherwise known as a solid torus. So sigma is a torus, and X is a solid torus. But topologically, there are many solid tori with the same ordinary torus boundary, because they differ by different ways of writing the ordinary torus as a product of 2 circles. The possible x's form a single SL2Z orbit, where SL2Z is the mapping class group of the boundary. So examples include thermal ADS, which is roughly ADS2 times a circle, but that isn't correct metrically. And also, importantly, the Euclidean version of the BTZ black hole. Now, for any one of these x's, it's possible to do an exact calculation of the path integral. The basic reason is that they're a single SL2Z orbit, so we only have to do one of them. And for thermal ADS, we can do the path integral because it has a Hilbert space interpretation. It's the trace in the Hilbert space obtained in quantization on D. But the only physical states are the boundary gravitons of Brown and Hinot, and their energies are completely determined by Virasoro symmetry. So we can compute the trace. We simply sum over all the model ranges of the resulting function. So a few things went wrong. So, well, one thing that went wrong is that the sum doesn't really converge. So we had to regularize it, and one could discuss whether the regularization was correct, but for today, let's assume it was. Beyond that, if there is really a boundary CFT, its partition function in a sector of fixed spin should be a discrete sum of exponentials, where E, N, comma, J are the energies of primary fields of spin J. Maybe, okay. But the function that we found was not of that kind. It was more similar to a continuous integral over energies rather than a discrete sum. At the time, we did not consider that physically sensible. But from the standpoint of today, that might be interpreted to mean that the dual CFT is really some sort of random ensemble of CFTs. Well, even if you had pursued that interpretation, there was something else a little wrong with our formulas. For j equals 0, we had a sort of delta function contribution that came with a negative coefficient. So we wanted a delta function, but we didn't want a delta function with a negative coefficient. This delta function was close to, but slightly below, the classical threshold energy of the BTZ black hole. At the time, all we could really say was that if 3D Einstein gravity is a sensible quantum theory, then there are additional contributions to the path integral beyond the known contributions that we had evaluated. We didn't really have any compelling ideas for what additional contributions there might be. I should mention a later paper by Maloney and Keller with more analysis of these functions. Now, there was an interesting advance rather recently by Benjamin, Ugri, Xiao, and Wang, which enriched the story in an unexpected way. And this provided the background for the work of Maxfield and Turiaci. The BTZ black hole has a threshold energy classically at energy equals J. So in this definition of energy, the ADS2 vacuum is at minus C over 24. So zero energy, the black hole threshold at angular momentum 0 is at energy 0, but that's above the threshold by a large amount, C over 24, or C over 12, counting left and right movers. But then if you add angular momentum, the threshold energy is not 0, but J. And Benjamin et al. Showed that for odd J, very near threshold, the density of states that would be inferred from the function Maloney and I calculated becomes negative. Roughly speaking, you get an exponential with the square root behavior near threshold. But then and this is, exponential is big in the following sense. S0 is the extremal entropy of the BTZ black hole of spin J. It's of order 1 over G Newton. So for weakly coupled gravity, it's exponentially big. And then there's a correction that's exponentially smaller, but is more singular near threshold. So since the leading term is positive, this sum is exponentially small, the sum is positive except very near threshold. But very, very near threshold, the second term can dominate. And so if A1 is negative, positivity is lost very exponentially close to threshold. And in fact, A1 is negative if J is odd. A1 is -1 to the J of J. So the first term has the usual square root behavior of a Hermitian random matrix model. But the second term is wrong. It's too singular. And in particular, it violates positivity. I'm sorry, it's too singular whether J is even or odd, but when J is odd, it violates positivity to boot. So Benjamin et al. Were not thinking about a Hermitian matrix model, but they did want positivity. So the problem they pointed out was that A1 can be negative, violating positivity. Their interpretation was roughly that the formula, something like this should be valid for a generic CFT at sufficiently large energies. But Maxfield and Turiaci observed the following. First of all, exponentially close to threshold means that the temperature should be exponentially small and the inverse temperature exponentially large if we're going to get exponentially close to threshold. So in other words, if we want to probe this behavior by a path integral, beta is exponentially large. Now, beta is the ratio of the two lengths of the two circles in a torus. So we should be studying the CFT on a torus in which one circle is exponentially bigger than the other. So let's think of the big one as having a size of order 1, while the second one is exponentially small. That's an appropriate situation for Kaluza-Klein theory. You can look for contributions to the 3D path integral in which the 3 manifold X everywhere has a very small circle. It's fibered over 2 manifold Y, with the fibers being circles of very small radius. Now in this limit, JT gravity reduces essentially to in this limit, in the Kaluza-Klein limit, 3D Einstein gravity reduces to 2D JT gravity, with the radius of the small circle being related to phi. Well, it reduces roughly to 2D JT gravity. It's a more complicated story. In fact, one of the questions I was asked had to do with the fact that Kaluza-Klein theory gives something a little more complicated. The topologies that Maloney and I studied by definition admitted classical solutions of the Einstein equations, since what we did was to evaluate the contributions of all manifolds in which we could solve the Einstein equations. What happens when we reduce our contributions to an effective 2D description by something like JT gravity? Maxfield and Turiaci observed that when we do this, we get JT gravity with conical singularities. The conical singularities look like R2 mod Zn, where n is an integer at least 2. So they have very special deficit angles, 2 pi times 1 minus 1 over n. That was why I asked Velotia if special deficit angles were not in construction. Why? Because the U1 symmetry that rotates the Kaluza-Klein circle can act in what's known as a semi-free fashion, meaning that a finite subgroup of U1 can have fixed points. Which value of n arises depends on which 3 manifold X we start with. But for some of the manifolds, for most, I should say, of the manifolds that that Maloney and I studied, if we reduce to 2 dimensions, we get a conical singularity. Maxfield and Turiaci observed that the computation of Benjamin et al. Could be interpreted as follows. So Benjamin et al. Had studied this function, which is the limit of the function Maloney and I had. They observed that in the effective JT description, the first 2 terms arise from a disk and from a disk with a single conical singularity. In JT gravity with conical singularities, these are the only cases in which you can solve the classical equations. So they're the only contributions you'll get if, like Maloney and I, you only evaluate contributions to the path integral from sectors that admit a classical solution. Now, from the point of view of random matrix theory, the second term is problematical even when it's positive, because it has the wrong threshold behavior. You expect the threshold behavior E minus E naught to the 1/2 for some E naught. In the purely two-dimensional discussion of deformed JT gravity, we had the same problem whenever U of 0 is non-zero. And the problem was cured by adding terms of higher orders in U and interpreting the result in terms of a shift in the threshold energy. Maxfield and Turiaci propose a similar solution to the problem found by Benjamin et al. In 3D gravity. In the near extremal region, it's natural to consider arbitrary Kaluza-Klein contributions, whether you can solve the classical equations or not. By Kaluza-Klein contribution, I mean that the 3-manifold X is fibered by very small circles. So mathematically, that means it's a general Seifert manifold with a U-on action, which in general is only semi-free, that has very small orbits. Then the quotient X mod U1 is a 2-manifold in general with conical singularities, and their contributions reduce on Y to JT gravity with a gas of conical defects. As we discussed in the purely 2D setting, such a gas of defects modifies the density of states and shifts the threshold energy. So the proposal of Maxfield and Turiaci is that the function whose non-positivity was pointed out by Benjamin et al. Is actually the first two terms in an expansion of something that looks more like this, with an exponentially small shift in the threshold energy. Higher order terms in the expansion come from Seifert manifold, whose topology is such that the classical equations cannot be satisfied. The proposal restores that there might be some sort of reasonable theory of pure Einstein gravity in 3 dimensions, dual, however, to some kind of random ensemble of conformal field theories, rather than to specific conformal field theories. Thank you.
Thanks a lot, Edward, for that wonderful talk. So maybe we can all unmute ourselves and clap. And we can now take more questions.
Can I ask a question?
Sure,
Edward, I missed some of the important points, so please excuse me, I want to just clarify them. In the case where U0 was 0, I think you said that after the first correction, the higher order corrections can be shown to vanish, is that right?
Yes, to all orders of perturbation theory.
I see. That seems very non-trivial, or I mean, is there some analog of localization, or how does that?
Oh, I'm glad you like it. I liked it too. Okay. I prove, see, any higher order contribution comes from this kind of manifold here. Mm-hmm. So you need the volume of this. You need the Weil-Petersen volume of this thing. Mm-hmm. And from very general properties of those volumes, you can prove the statements. So if B is the radius, sorry, the circumference of this circle gamma, the volume is a polynomial in B of order, I think, n-1 or n-2 or something, where n is the number of singularities. And I think the constant term in that polynomial vanishes. So you can actually compute those polynomials, but that's more complicated. But it's rather easy to prove that the volume is a polynomial with some restrictions on the bottom term. And just using that, you can show that all the corrections vanish if U of 0 is 0.
I see. Okay.
So it's not, I haven't in this lecture explained all the facts you need to know, but the proof is not very difficult. It's in my paper.
And then if I can just ask a related question, in that for the case where U0 was not 0, yes, I mean, as you mentioned also, from the gravity point of view, you might think that in that case, you don't have what's called attractor behavior, and you change the near horizon geometry in a more significant way. And I was just curious whether, did you show then that after summing the threshold corrections, there is a random matrix interpretation?
Sort of, and Maxfield and Turiaci showed it even more. So yes, okay. What the question means is if we go to higher genus, or sorry, even, okay. From the disk, we computed what rho of E has to be if there is a random matrix interpretation. And then, so what your question means, I'll give a couple answers actually. So the most direct answer to your question in the spirit of the lecture is now we should calculate something else. For example, an annulus amplitude, or we could have a three-hole sphere, or we could have a higher genus topology. And once we have a random matrix with a known rho of E, we know what the amplitudes have to be for those higher topologies. So I computed a number of them, and all the ones I computed agreed with random matrix theory. And Maxfield and Turiaci computed more. But actually, if you use, this is not in my paper. Okay. Okay. Using the proof by Kontsevich, Mirtakani, and others of my conjecture from 30 years ago about topological gravity, and using general factors about Weil-Peterson volumes, you can show it's got to be true. But I didn't give an abstract argument like that in the paper. In a sense, Maxfield and Turiaci did, because they did give a general proof, but their general proof relied on mathematical theorems, which ultimately go down to the validity of that kind of conjecture. So, okay, to give you a quicker answer, you can calculate examples without too much difficulty of higher topologies and show they agree with random matrix theory. But you can also give a general proof using general theorems about volumes. That's the quick answer.
Thank you. Thank you very much.
Sure.
I have a question, Edward.
Yes.
So if one looks at this paper of Einard and Orentin, then the matrix model that is mentioned there is this Kontsevich integral, which has these, this has a matrix lambda, which is an arbitrary matrix to begin with. All these matrix models, which are, what shall I say, which correspond to the models that Saad, Shenker, and Stanford, and yourself, and Maxfield and Turiaci have been working on, would they all correspond to looking at the same Kontsevich integral with different values of lambda?
No. It's a Hermitian matrix model. Okay, sorry. The language that Einard and Orentin use is rather abstract, I guess because they're mathematicians. So they don't say, it's a physicist's interpretation of what they proved to say it the way I did. What they have this thing that they call topological recursion,
yes,
which holds for a spectral curve.
Yes.
And they don't want to call it a matrix model because from their point of view, they don't know rigorously that there's a matrix model related to a given spectral curve.
I see.
As a physicist, you'd probably be less bashful. So I'm really bad at trying to write on this thing. So as a physicist, oh, it's not even working. I wonder why that is. I think I think in order to write, I think I have to share a different screen, the whiteboard.
Yeah, you should go to the whiteboard.
That works. Although I'm so bad at writing on the screen that it might not be helpful. I might have done better. So you have a function of the matrix. I'm calling the matrix H the Hamiltonian.
Yes.
And then you compute a density of eigenvalues.
Yes.
Then there's a spectral curve.
Right.
It's y squared equals minus rho of E squared.
Right.
Now, Einard and Orentin study spectral curves, and they have topological recursion for an arbitrary spectral curve. To them, it's not rigorous that an arbitrary spectral curve comes from a matrix model, even though a lot of them do. And so they state their results, they express their results. Okay. In the paper where they made contact with the work of Mirzakhani, what they said was that there's a particular spectral curve where topological recursion leads to Mirzakhani's recursion relation for volumes. So that spectral curve was the one I've written here, with rho being the appropriate rho for JT gravity. Gosh, it's so hard for me to write it. Well, I'm leaving out a lot of factors because it is hard to write.
Yes,
but
yes, I understand.
So what the Eynard-Orentham explanation of what they proved was that for this spectral curve, what they call topological recursion reproduces Mirzakhani's formulas for volumes. Now, if you're a physicist and you're willing to assume that, like every other spectral curve, this one comes from a matrix model, you just say that there's a matrix model that leads to this spectral curve, and that's the matrix model that's behind JT gravity. Now, I don't think that's been done carefully. Well, if you, okay, how would you do that? Well, first of all, okay, JT, okay. Suppose you took the minimal models. So Saad et al. Argued formally that the JT gravity was a large p limit of the 2, 2p+1 minimum model.
Yes.
That's actually been recently used by Clifford Johnson to get non-perturbative results on JT gravity. Quite fascinating, actually. He's giving a talk on it Monday at the Institute, which is supposed to be on this calendar, but when I checked this morning, it wasn't. Anyway, so for the 2p+1 matrix model, people worked out the matrix model where, in the old days, people found the matrix model that corresponded to the spectral curve of the 2p+1 matrix model. And the large p limit of that would be the matrix model that leads to JT gravity. I'm not sure that anybody has carefully analyzed whether you literally can take the large p limit of that matrix model. Okay. Anyway, the reason that Eynard and Orentham expressed their results in ways that are do not sound as simple as what I say, for example, is that from their point of view, it's not rigorous that the spectral curve came from a matrix model.
Okay, thank you.
I have a question, please.
Sorry, Shiraz. I see Gautam's hand raised for a while. Can I ask him to unmute himself?
Yeah. Hi, Edward.
Hi, Gautam.
I have a question about these multi-cut matrices, matrix models. So 2 questions. One is that, so of course, the matrix models are given by some integral over exponential of minus n times f of h. So there's the function f. So presumably those will be characterized by your alphas and epsilons, which are in the u function. So can these functions f of h be computed explicitly by sort of inverting the resolvent method or some other way?
Well, that's not completely unlike the answer to Spence's question. So it's so much easier to work directly with the spectral curve than to try to figure out what matrix model really led to that spectral curve. That's what people tend to do, at least in a lot of recent papers.
I see. So,
in general, though, there's no problem. So there's no problem to find matrix models that lead to multi-cut solutions. If the function f of h has several minima, then there are several places where the eigenvalues will tend to be. And then you can get a solution with several cuts.
Yeah, so that I'm aware of. So in the old days of Hermitian matrix models. So
but many people,
yes,
our younger colleagues who are on the call would not be. That's why I wanted to explain it a little bit. So for those who weren't active in the earlier period, if you simply take a function with several minima, you're going to tend to get a multi-cut matrix model.
Right.
Anyway, go ahead. Gautam?
Yeah. So so first of all, there will be presumably this hierarchy of phase transitions, depending on so the minimum the structure of minima could be quite involved, and there could be a hierarchy of phases. And I just wondered whether there is a dual gravity interpretation of these multi-cut phases or the phase transitions.
Well, I expect there is, but I don't know how to approach it. I think it would be really interesting to understand bulk duals of multi-cut matrix models.
Right. Okay, thank you.
There's something else that sounds easier, but I also have trouble with. Even within single-cut matrix models, there can be Hawking-Page transitions where the vacuum changes, or if not the vacuum changing, at some given temperature, the stable black hole can change. And I had trouble, it would be nice to figure out in JT gravity or something similar to JT gravity, how to describe those phase transitions. I didn't have much luck yet, but anyway.
So what kind of difficulty are you talking about?
Well, Coleman famously back in the 70s, Coleman and Callan wrote about the decay of the false vacuum, where a bubble forms. You have an unstable vacuum in a Minkowski space. A bubble forms and expands to infinity at the speed of light.
Yes.
I think it would be nice to have it would be a tunneling process, but okay. If you have an unstable black hole that decays to a more stable black hole, I'd like to see a tunneling process where a shell of matter goes out and you're left behind with a more stable black hole. So that would be a kind of dynamical version of the Hawking-Page transition. Hawking and Page originally just said that in equilibrium statistical mechanics, there's a phase transition, but that should happen dynamically. If you go to the metastable region where your original black hole is not thermodynamically stable, there should be an event somewhat like the Callan-Coleman process, I imagine, where a shell of matter goes out and you're left with a more stable black hole or something. So I thought JT gravity maybe was simple enough that you could make that explicit. I tend to think you can, even though I haven't been successful, but anyway.
Right. I mean, there is another version of, I mean, the Gregory-Laflamme phase transition is another context in which, there is a sort of transition between eigenvalue distributions, similar to the, the Gross-Witten transition. And so there is a dynamics known as well as a thermodynamics known, that you have an onset of instability and
yes, but that's a second. The reason that dynamics is known is that it's a second order transition. So there's a smooth onset of instability.
Ah, yes.
I think some of these other things are first order transitions.
I see. Okay, thank you.
Sure.
Okay, maybe Shiraz, maybe you can ask a question.
I had a couple of questions. First one is just to follow up on what you said about the Hawking-Page transition. Given this density of states here, we could compute the temperature, as a function of energy, just from the matrix model. And for the Hawking-Page transition to happen, that would have to be sort of a multi-valued function.
Yes.
Does that happen in your density of states?
That's well, not generically. Oh, well, it doesn't happen in JT gravity, so it doesn't happen in anything sufficiently close to JT gravity. If you go far from JT gravity, you can make it happen. In other words, what I discussed with that sum of exponentials was rather general. So you can make, I didn't check this carefully, but I would imagine you can do practically anything with that kind of function. In other words, even though it's, sorry, this was supposed to be epsilon. Even though it's not literally true that you can write every function like this, gosh, having even more trouble writing. Anyway, an awful lot of functions are sums of exponentials. So in a limited range of fields, you could make it do anything I expect. And only a limited range of fields is important for your question. Something I want to point out, though, is that so Hawking and Page treated the black hole classically. And for that to be valid in JT gravity, you have to go to high energies, in other words, high temperatures. So in what I've been discussing with the alphas being positive and epsilons of order 1 at high, well, okay. You'd have to choose a potential where you can go to energies which are large enough that a classical description of the black hole is valid, and also still small enough so that the perturbation away from JT gravity is important. But definitely you can dream up a potential which would make that happen.
And your comment about this expanding shell was in the context of such a thing.
Yes. Well, that's what the answer I wanted to get. Yes. I wanted to make a model where you could see the first order transition as a dynamical process.
I have a second more general question.
Yeah.
In more familiar examples of the ADS-CFT correspondence, when we look for the dual of a gravitational system, we try to write down a Lagrangian, then perhaps a Lagrangian with some random coefficients, and then quantize that Lagrangian and get a Hilbert space, and get a Hamiltonian. Here you seem to be just directly telling us what Hamiltonian to the dual system is, and perhaps the statistics of Hamiltonian, without going through the intermediate step of writing down a Lagrangian or a simpler description whose quantization gives us this Hamiltonian. And I was wondering whether the reason for that was that there are no more interesting boundary observables in this theory than just partition functions.
Well, that's sort of true.
So perhaps I could ask, would you expect there to be a more a second level, an intermediate level description of the boundary system, which is some sort of quantum mechanical system that would give you this Hamiltonian, whose quantization would give you this Hamiltonian, rather than just stating what the Hamiltonian and statistics is in the context of JT gravity?
Well, I mean, in higher examples of dualities, like suppose we do ADS 5 times S5, I'm not sure what you would want to say there. On the boundary, we say that the theory is n equals 4 superring mills. In the bulk, it's type 2b superstring theory. And then we just say those two are equivalent. Here, the claim is that JT gravity with these exponential perturbations is dual to a certain random matrix theory. The fact that it's a random matrix theory rather than a specific quantum system is different from the higher dimensional examples. But what's so different?
Well, I was thinking, in the case of n equals 4 Yang-Mills theory, we don't specify the dual by giving the Hamiltonian of n equals 4 Yang-Mills theory directly. We give a more elementary description.
Okay, that's right. Well, well, if we had a specific Hamiltonian we were trying to get, you might ask, is there a natural classical system whose quantization gives that Hamiltonian? But since it's actually a random Hamiltonian, well, at a minimum, it would have to be a random classical system. Yeah, I think that's going to be hard. I doubt there's a different, okay. Well, similar to in spirit to what's known now, I doubt there's a different way to do it.
Could I ask, do you expect there to be additional observables in the system other than partition functions? Something like insertions of something on the boundary.
Well, it's hard to think of, if you're asking for local operators in the boundary, that's hard to think of. Saad, Shenker, and Stanford discuss things such as the determinant of E minus the Hamiltonian, which is related to D-branes in JT gravity.
So is the lack of the fact that there are no local observables on the boundary, is that the reason why one should expect not to have this more elementary sort of local description of physics, local in time description of physics, rather than just taking the Hamiltonian? Sorry, I'm sorry for asking so many questions. I'll stop.
Well, you could, I think we should go back to the JT description and try to see if we can think of local observables we want to ask about. So phi is specified on the boundary. The trouble is that both phi and the induced metric are specified on the boundary. Right. Yeah. Any observables in the boundary involve normal derivatives of the metric or of phi, perhaps higher derivatives. Well, I mean, the Schwarzian density, corresponds to the Hamiltonian, after all. Look, maybe I should tell you that the Schwarzian action is the answer to your question. So the Schwarzian action is a boundary path integral that you can study to get this density of states. Yeah, I think we'd have to give you that answer.
And is that a non-perturbative answer? Does that have all the features of the matrix model? Well, approximately.
No, it really just gives the bulk path integral on the disk, or the trumpet, and well, a few other topologies if you change the rules a little bit. But right, yeah, okay. It doesn't know about the higher topologies. Okay, I don't think an answer is. Yeah. Okay.
Can I ask a question related to this? I mean, is it possible to think about the connection between random matrix theory and n equal to 4 Yang-Mills theory in the following way? That if we actually, by some method, are able to compute the spectrum of n equal to 4 Yang-Mills theory at large n and large values of the 't Hooft coupling, so that in some sense it corresponds to the spectrum of a dual black hole. Yes. Then a lot of people have sort of mentioned that such a spectrum actually would represent the spectrum of random matrix theory, the eigenvalue distribution and the statistics of the spacings, etc. Would that be a way in which random matrix theory will enter n equal to 4 Yang-Mills theory in terms of just the spectrum?
Well, presumably it's true that that statistical properties of the spectrum would match random matrix theory. But n equals 4, we think, is an actual Hamiltonian, not an ensemble of Hamiltonians. I think the situation is probably roughly that if you have imperfect knowledge of the bulk theory, it will appear to be dual to a ensemble. But if you have perfect knowledge of the bulk theory, it would correspond to a definite bulk theory like n equals 4 super Yang-Mills. That's a guess, approximate guess.
Nice. Okay.
I don't have any way to make it concrete. So there's the paradox in ADS-CFT and Euclidean signature that you can make what appear to be connected correlation functions between two boundaries. They should vanish when there's a definite theory. And I can't suggest the mechanism by which they vanish.
I see, okay. Means no wormholes, basically.
Well,
sense.
no wormholes connecting different boundaries.
Yes, yes, that's what I meant.
Doesn't say that there can't be wormholes connecting a boundary itself. A long time ago, about 20 years ago, with Yale, we were bothered by this problem, and we wrote a paper trying to get rid of it, which didn't succeed. All we did was restrain it. We showed that if the boundary, we were motivated by positive scalar curvature, because n equals 4, and so many of the simplest examples of ADS duality have the property that the boundary CFT is unstable if the boundary doesn't have positive scalar curvature. And then we showed that if the boundary has positive scalar curvature and the bulk satisfies Einstein's equations with negative cosmological constant, there can't be a wormhole. So that's a true fact. And it was motivated by trying to get rid of this problem, but it didn't really get rid of the problem because of various reasons. One is that although many of the boundary CFTs are unstable if the scalar curvature isn't positive, it's not true that they all are. That's one issue. And secondly, if you include suitable sources in the boundaries, the conclusion would be modified.
Thank you.
I think Abhijit is in line to ask the next question.
Hi, Edward. I have a couple of questions on the last part of the talk. So this proposal of Maxfield and Turiaci, does it also address the delta function like singularity with a negative coefficient that you and Alex had observed?
That hasn't been addressed, but it's once you assume that there are additional contributions from non-solutions, it's less of a problem. Because in the regime of Benjamin et al., which is near threshold with non-zero angular momentum, you can identify a restricted class of geometries. Well, okay. It's not known how to address it, but it's also not known what geometry should be included. Once you're including non-classical geometries that don't have classical solutions, so they're unknown contributions, it's out of control. So the regime of non-zero angular momentum exponentially close to threshold, it's plausible that that's the regime of Kaluza-Klein theory. And maybe it's true that Seifert manifolds are all you need to consider. And it does look like they get rid of the problem in that regime. So for the other regime you asked about, where the angular momentum was 0, it's not known what you should do, and it might be more complicated. That's the answer that Maxfield gave at the strings meeting, I think. That's the answer they say in their paper, actually.
Okay. And also, so this, just to understand the Seifert manifolds a bit better. So let's say the reduced theory, you have two conical defects.
Yes.
In 3 dimensions, it's supposed to be a smooth topology, in a smooth geometry. And what kind of topology is it?
Well, if you understand the case with one conical singularity, it looks like that locally. Okay. So, right. Okay. I'll tell. Yeah, there's an easy answer. You start with R2 times a circle, and then you divide by Zn. Zn acts by rotating the circle by an angle 2 pi over n, and rotating R2 by the same angle, or a multiple of the same angle in general.
Mm-hmm.
Now, this action is called semi-free. Oh, sorry. Okay. There's a U1 symmetry. Let me say it a little bit differently. Yeah. Okay. Here's another way to say it. There's a U1 symmetry on the problem. It rotates the S1 with charge 1, and it rotates the R2 with charge n. The charges don't have to be 1 and n, but 1 and n is a good example.
Mm-hmm.
Sorry. I'm trying to say 2 different things at once, and it's causing a trouble. Let me answer your question first. to answer your question was what the singularity looks like. Oh, sorry. Your answer was what's the three-dimensional geometry that looks singular in two-dimensional terms? So we do include Klein theory. Well, I start with R2 times the circle, but I divide by the Zn I told you. It rotates both the circle and the R2 by the angle 2 pi over n, for example.
Mm.
Now, that's a smooth geometry. It acts freely because it acts freely on the circle, right?
Yeah.
As a three-dimensional geometry, it's smooth. But now suppose the circle is very little, and we do Klein theory. That means we make an effective two-dimensional geometry where we forget the circle. Then we just have R2 divided by Zn with a conical singularity at the origin.
Right.
So the three-dimensional geometry is smooth, but the two-dimensional geometry has a conical singularity. So this is the local picture near any conical singularity.
I see. I see. Okay. And I see. And as for the topology, is it I see the boundary is always a.
The boundary is always going to be a circle.
Yeah.
To draw the two-dimensional geometry, it's got a certain number of these conical singularities. But in 3 dimensions, there's another circle that's very small, so it's hidden in this picture. And near each of these points, you have the local story that looks like this.
I see.
R2 times the circle.
And if one wants to extremise the action in this configuration, somehow the singularities all come together and giving rise.
If you try to extremise the action, yeah, there's no classical solution except by letting them come together.
I see. Thank
And
you.
even that would work. For some values of the integers, I think you can't do that either.
Right. Thank you.
Okay, if your question is done, Abhijit, then maybe I can call on Rajesh.
Yeah, hi, thanks. I also had a couple of questions. The first one is along the lines of what Gautam Center were asking earlier about this, the form of the matrix integral, the f of h, which gives the gives this density of states. So even without, let's say, the deformations, do you think there could be a combinatorial interpretation of that matrix integral directly giving rise to these volumes of moduli space, somewhat like the Spener matrix integral gives rise to the Euler character and so on and so forth, and it does it in a sort of a combinatorial way. Do you think that that could be, or was that maybe something that the mathematicians had how Mirzakhani and others had come at this?
I don't think anything quite like that's been done. I don't know if it could be. What Mirzakhani did actually is reviewed in my paper with Douglas Stanford from last summer, and I'll talk about it at the strings math meeting. It's a little bit hard to explain in a few words, but it had to do with chopping Riemann surfaces into pieces in a clever way. Anyway, the quick answer there was that nothing like that is known.
Okay, but I mean, do you have any sense of whether there could be a combinatorial interpretation, given that you're computing something intrinsically on modular space, and you could think of some matrix integral which does that in a combinatorial way? Do you think it's related, or is that one would think there might be some meaning to that matrix, that f of h and that integral?
Well, I don't know. That's the only real answer.
Okay, then maybe I'll ask the second question, which is a bit more kind of it's a little more vague question, but the three-dimensional the three-dimensional contributions that you mentioned of Maxfield and Turiaci, you could see these first two contributions as coming from these classical solutions, but in general, you might the speculation is that that there's something that corrects the whole series, but are not classical solutions. But could it be that there again there is some sort of a recursion relation of volumes, similarly to, I mean, it's the lift of the volumes on ordinary, so here you're computing hyperbolic, the volumes of hyperbolic spaces in 2 dimensions. If you lift the volumes of hyperbolic manifolds in 3 dimensions and try to, so do you think there could be a geometric interpretation directly in 3 dimensions if the, of which these two are the terms? Is that?
Well, so the Maxfield Turiaci proposal is that Klute-Klein contributions, 3 manifolds with a small circle, are the ones that solve the particular problem of Benjamin et al. So they did have 3-dimensional interpretation.
Yes, but that 3-dimensional interpretation, could one view it like in an intrinsically in terms of an intrinsically 3-dimensional, I mean, a volume, just like the 2-dimensional interpretation was in terms of 2-dimensional hyperbolic volumes with boundaries and conical defects. And so
I think your question is there a 3-dimensional way to calculate the path integral?
yes,
For those
in terms of, so, okay, just to be.
There might be, sorry to interrupt you. The manifolds in questions are called Seifert manifolds. They're not hyperbolic, by the way. That's related to the fact that you can't solve the classical equations. So they're 3 manifolds, but they're not hyperbolic 3 manifolds. They are Seifert manifolds, which just means that they have a circle action where a U1 action where there's no fixed point of the whole group, although there can be fixed points of Zn subgroups. And Chern-Simons theory in 3 dimensions on a Seifert manifold can be, the path integral can be computed by localization. That's actually, well, for ordinary Chern-Simons theory on a compact Seifert manifold, Chris Beasley and I wrote a paper on that about 15 years ago. In terms of purely bosonic Chern-Simons, but some things were understood better later in terms of localization and super Chern-Simons. Anyway, it's not impossible that that could be done for gravity. But that's far from doing a complete 3D gravity path integral. 3-dimensional gravity understood as a sum over all 3 manifolds seems awfully complicated. For instance, here we're discussing 3 manifolds that aren't hyperbolic, but most 3 manifolds are hyperbolic, and there are an awfully large number of hyperbolic 3 manifolds.
Yeah, what you said about Chern-Simons theory, I mean, I was wondering whether there was something in terms of volumes of flat connections, something analogous to the JT gravity computing computing these volumes. The higher dimensional analog of that, perhaps from a Chern-Simons like point of view, would be perhaps in terms of
well,
connections.
As I said, in Seifert manifolds, for ordinary Chern-Simons, localization gives something roughly like what you're saying, and it might generalize to gravity. That's Seifert manifolds. That's not; those are not generic 3 manifolds. Generic 3 manifolds are hyperbolic 3 manifolds. On a generic 3 manifold, ordinary Chern-Simons is still solvable, but not by localization.
Okay.
Okay.
Okay, I think the next person in line is Clifford. Maybe I can ask Clifford to unmute his mic and ask this question.
Hi, thank you. Thanks for a nice talk, Edward. And also for very kindly mentioning my work and my talk coming up on Monday. So I will there as a little plug try and unpack in some detail how you can use minimal models to push all of this in interesting directions. I had a couple of remarks and then a question about your opinion on a certain perspective. So one remark, you were talking about, it would be nice to understand Hawking page-like transitions in JT gravity. And you probably know this, but at least one toy sector that you do have control over is for example, comparing you know, in the 2-point function of the partition function, so just sort of 2 boundaries, you can watch and evaluate the relative action of 2 disconnected pieces, which, if you like, are 2 black holes, versus the transition versus what would be the connector geometry, the wormhole. And you can see how one hands over to the other, for example, if you're computing the spectral form factor. So that's sort of a baby version of that sort of picture, which is somewhat explicit in the JT calculations that are possible. And you can see that in matrix models as well. So that's one comment. And then,
But I was still hoping to see a dynamical process, more like the Kalman-Kellen process.
Yes, yes, yeah, no, yeah. Well, I
haven't I think I need to do that.
Yeah, I agree. That's much harder, but I was just saying there are some sort of fragments of that sort of reasoning going on already. And then the other thing I wanted to mention, and this I'm sort of puzzled about, and this is sort of, you know, really trying again, what lessons can we learn that will extend to higher dimensions? And there is something very special going on in 2 dimensions, and which I'm not sure if you have an opinion on this. I'd like to understand it better. And it's just this business that if, and again, speaking as a sort of veteran of the 90s matrix model time, you could, with hindsight, go, well, as soon as I have 2-dimensional gravity and perhaps some large class of 2-dimensional gravity, which includes things we've seen with the minimal models, the minimal strings, and also now JT gravity, you could go, I'm sort of guaranteed to have this averaging picture, just from the sort of simple-minded perspective that I have that old Tufts type language that tells me that if I sum over random surfaces, it's equivalent to tessellating 2-dimensional surfaces, getting a topological expansion, and then of course we take a double scaling limit to get the nice smooth surfaces. So somehow there's as soon as you have a 2-dimensional gravity in the game, perhaps you always have a matrix model, and so you always have that sorry, not randomness, that averaging. And of course, that doesn't generalize to higher dimensions. So I'm trying to understand and come to grips with to what extent what we're seeing is just a very special aspect of 2-dimensional gravity, and if I have a 2-dimensional gravity dual, or if, you know, there are parts of it that could still make sense in higher dimensions.
Well, I don't know, of course, but 3D gravity does seem like it's, again, not going to be dual to a particular conformal field theory, but to some kind of ensemble. What troubles me, though, is that it might not be possible. That statement, if it's true, is more interesting if you can give an independent description of the ensemble. And I'm not totally sure you can. I'm at a loss for how to do it, but maybe you can. Above 3 dimensions, well, okay, I think part of what we're learning is the following. Okay, if you just have a bulk gravity path integral, you can construct from that a lot of the structure of the boundary CFT. But it's more clear now than it was in the past that you really are not constructing a full boundary CFT. So you can define local operators and their short distance behavior and so on, if you have a bulk path integral, by taking boundary limits of bulk operators, roughly. But you don't really get the full non-perturbative structure of the CFT on the boundary in general. And the example of JT gravity shows that dramatically. In cases where we know what the boundary theory is, like n equals 4 0 per angles, then there is a boundary dual. If you somehow could construct a gravitational path integral by hand, sort of, in a way that gave no insight about what the boundary was, well, that might be a candidate for a conventional boundary dual not existing. In higher dimensions, though, our only reasonable constructions of gravity path integrals are related to string theory and tend to come with advice showing that there is a boundary theory. Not that I'd claim we know everything perfectly, but that would be my guess. I'm not sure if I'm answering your question anyway, but I probably can't.
Well, thanks. It's one of these things where we as happened with two-dimensional minimal strings, etc. With 2020 hindsight, decades later, we understand what the lessons are they were trying to tell us, and it might be happening again. And but I'm still stuck on this point that somehow in the two-dimensional case, we sort of all in this general sense that there ought to be something like a random matrix model which tessellates the surfaces and tells us how exactly to do the path integral over all the random geometries. It is a random matrix model just by construction, and so it just seems like I just can't get away from deciding, knowing whether to decide whether that's a two-dimensional accident gift that's just strictly two-dimensional, or that's just happens to be the way that the two-dimensional problem solves itself, but some other structure takes over in other dimensions that we just don't yet have as much control over. Hopefully it's the latter. Anyway, that's all I had to say.
Yeah. But even in 2 dimensions, we have a problem that if we add matter fields, we don't know anything quite similar.
Yeah, that's true.
Actually, yeah, sorry to butt in, but Edward, after Clifford is done, I wanted to ask you about exactly that, whether you think some of this might change for generic matter. For example, the double trumpet maybe really doesn't get connected if you have kind of generic matter because of negative energy blowing up at the throat. Anyway, I'll wait my turn. I think I'm after Clifford and Schumett, sorry. But in case you want to comment on matter more.
Well, I was going to mumble some things about non-perturbative physics, but I think I will yield the remainder of my time to Sandeep.
Oh, well, what? I leave it up to Ed.
Well, regardless, I don't have much to say about.
But just to rephrase, do you think 2D gravity with matter will again generically have a statistical interpretation, or could it be that there, once you add matter, at least in a sufficiently large class, you don't have this kind of statistical interpretation?
I feel that if you define something purely from the bulk point of view, that you construct by hand a gravity path integral, for example, you add some scalar fields to JT gravity.
Yeah.
I think with what we know now, you should be skeptical of expecting that there's a boundary CFT. Sorry, boundary quantum mechanics would be in that case.
Yeah.
Could one make any sense of it as an ensemble? I'm not sure. That seems like a good question.
Okay.
But now we're in the situation that I think I was asked about before by Shiraz, where very conspicuously there are lots of boundary operators we should worry about.
Right.
I'm afraid I don't have anything useful to say.
Okay. Thank you. Thank you. Sorry, Clifford, if I interrupted. Okay, I'm done.
Okay, if Clifford, you're done with your questions, maybe I can ask Sumit to unmute his mic and ask his question.
Yes, I'm finished. Thank you.
Okay,
Hello,
thank you.
sir. I have a very naive question. Is that relevant here to further generalize this deformed JT gravity model by adding GS fields like Maxwell and Young's field?
Adding what? I didn't hear you.
Adding new fields, just like a Maxwell field. GS field.
First of all, when you start from 3 dimensions, there is a Maxwell field in 2 dimensions. So the Maxfield Turiaci paper does have one. And they do a little bit with it because it's related to the angular momentum. So Maxwell fields, more could be done, I'm sure, with JT gravity with Maxwell fields. But Maxwell fields have the property that they don't create local degrees of freedom in 2 dimensions. If you had scalar fields or fermion fields, which would be more in the spirit of some of the previous questions, then it becomes much harder to say anything similar to matrix model. Then I can't tell you much, I'm afraid.
Thanks.
The simplest idea, if you have a Maxwell field, you add a gauge field in the fork, then the boundary has a global symmetry. So the boundary quantum mechanics doesn't just have a Hamiltonian, it has a Hamiltonian and a global symmetry that commutes with Hamiltonian. And you do random matrix theory under those conditions. And that works pretty well.
Okay, thank you, sir.
Yeah.
Can I, there's one other raised hand by Raghu. Can I ask Raghu to?
Yeah, sorry. Edward, I just have a technical question. So you mentioned this restriction on U of phi that if U of 0 is 0, you get a nice answer. Is there also some restriction on the asymptotics of U at large phi?
Well, in the derivation there was, because alpha was between pi and 2 pi. So U of phi had to vanish exponentially for large positive phi. It could grow exponentially for large negative phi. Usually in JT gravity, large negative phi is cut off because the classical solution always has phi bounded below. So classically, we expect a condition at large positive phi, and the potentials were actually calculated, vanish exponentially there. However, the answer makes sense for more general U, and I can't make any guarantees about whether it's valid for more general U, but it might be.
Okay, thanks.
Emil had a question in the chat. I don't know if Emil is around and he wants to ask this question.
It was just a comment at the time of the discussion. I didn't have a question.
Okay.
Okay. Well, are we running out of questions, or are there still more?
I don't see any more raised hands. If anybody else has a question, maybe they can speak up at this point.
Any comments on de Sitter? Space in 2 dimensions. Sorry. It's sort of a natural question.
Yes, it's a good question, which I'm afraid I don't have anything to contribute to. I want to learn more about what people are saying, but I don't have much to say.
For example, if we took U of phi to be negative 4 phi, you could get the de Sitter potential because that would change the sign of the cosmological constant. So
Yeah.
you could ask whether it's valid.
This is a good question, but 2 technical comments. One, first of all, what Raghu was saying is this: I considered the case of the potential, which was 2 phi plus something. So he's saying let the something be minus 4 phi. And then classically, we actually would have de Sitter space. Well, there are two technical problems with this. One is that the function minus 4 phi is not in the class of functions that were allowed in the calculation. And those functions all vanish when phi goes to plus infinity, which minus 4 phi does not. The second problem is that you're reasoning classically when you say the 2 phi plus minus 4 phi is minus 2 phi, and then you want to treat the theory as JT gravity with minus 2 phi. But as I warned you at the beginning, we were defining the theory in a very particular way, which might not be compatible with what you're saying. But caveat emptor or buyer beware, you can go ahead and try it and see if you can get anything sensible by thinking along those lines. I'm not going to say you can't. I'm just going to say that for the technical reasons I've mentioned, it's not obviously correct as a way to probe de Sitter space, but who knows?
Okay, thanks.
Thank you.
Do we have any other questions?
Well, it's too bad we can't take Edward out for a good Indian meal at the end.
I'll take a rain check on that one. Thank
Please
you.
do.
I hope to see you all in person soon.
Yeah, right. Likewise.
And online sooner than that. At the next conference or maybe the next lecture.
Right.
Okay. Thank you again for the invitation.
Yeah.
Thank you
Thanks a
very
lot,
much.
Edward, for your
Thanks.
time. And you
My
can,
pleasure.
yeah, maybe unmute and clap again.
Okay. Okay. Thank you then.
Thank you.
Bye-bye.
Bye.